and welcome to PCB Chat, where we talk with experts across the printed circuit design, manufacturing, and electronics supply chain fields. I'm Mike Buetow, Editor-in-Chief of PCD&F and Circuits Assembly. Today's podcast is sponsored by Zestron Corporation, the leading provider of high-precision cleaning products. Be sure to visit Zestron at SMTAI Booth 623. This week, we continue our series called the Screwups. In these segments, we talk with experts in electronics manufacturing about specific problems they've encountered and offer up some potential solutions. And I'd like to welcome back our guest, Tim O'Neill. Tim has nearly 25 years' experience with solder materials, primarily at AIM Solder, where he is currently the Technical Marketing Manager. And I believe our problem on the floor today has to do with solder wetting. Is that correct, Tim?
That's correct, Mike.
So what do you have for us?
So this particular circumstance is still ongoing. So I don't know that we'll reach a conclusion here, but the topic will certainly be an interesting discussion point. We are often tasked with, as a solder supplier, providing evidence to our clients that a switch to an AIM product won't introduce any unintended difficulties, whether in terms of production, throughput, or quality. So a transition of chemistry in a production operation is often a very involved undertaking. And one of the pieces of evidence that customers request are cross-section of the solder joints that were formed using whatever flux or alloy or solder paste that we're actively trying to get approved. So in this case, it's a customer that is an existing client using a traditional lead-free alloy. We've marketed to them a alternative alloy. It offers some benefits in that it reflows at a slightly lower temperature and it's lower cost. So as a high volume manufacturer, a half a cent here and a half a cent there, when you're using 1 million or 2 million grams a year, can add up to significant cost savings. So they, pursued it with open arms, and we're in the final stretch of the evaluation process, and we performed cross sections on some of the assemblies. And what I noticed was on a particular component, a leadless package, a QFN style component where you have a ground paddle and these perimeter leads, was that the solder joint angle exceeded 90%. Now, as per 610G, the quality manual from ITC, a wetting angle of greater than 90% is considered unacceptable. In fact, they use the in bold shall not exceed 90%, which means they really mean it. So
I love the shall not.
Yeah, it shall not. I mean, it's pretty clear. Definitely not. It's not subjective.
Tim, as an aside, do you know that back when I was working at IPC, we actually included the definition of shall in the terms and definitions guide?
Well, considering the people that you were giving the information to, it was probably necessary. So, and that's not meant to be a slight, is that if it's not abundantly clear, it can be argued. And if it can be argued, we work with a bunch of people that will be happy to argue it with you. So that's why I say that, because they're all very bright and they see things differently, and a different perception of the rule book can affect outcomes. So shall not means shall not. So in this particular case, the results with the SAC 305 that was in use and the alloy that we were proposing, they were roughly the same. We weren't giving them a worse outcome. It's just that they hadn't cross-sectioned with the SAC 305 before because it was SAC 305, so nobody looked at it. Now they're looking, and they're saying, hey, wait a minute, we're not meeting the IPC criteria. So then the argument that's ongoing currently is it a pass? Because it seems as though on that particular device, because the termination is exposed copper and therefore a difficult to wet surface, that the rule shall be ignored. So a greater than 90% wetting angle is acceptable because the mating surface between the substrate and the component is a robust joint. It's clearly evident. We have a good intermetallic from the cross-section results, but it's this wetting angle that's the issue. So that's the debate that's raging right now. So when you ask me about wetting, this is the anecdote. So it brings up, in my mind, a host of other questions as it relates to wetting. And for the benefit of our listening audience, I'll just go through, and feel free to jump in at any time if you think I'm getting too far afield. Wetting conditions that really, some are obvious and evident, and everybody would agree that it's a defect, but there's a fairly large portion of these wetting defects that can be interpreted in a variety of different ways, and the root cause can be subjective as well, meaning what caused it. And I'll refer back to one of our most common issues. So, phone rings, customer on the line, your solder paste stinks. Well, this is the customer. Let me talk you off the ledge. What seems to be the problem? And they say, I've got this one component that I just can't solder. It's, practically I can pick it off with my finger. And from there, the conversation starts. So usually in my head, I don't necessarily articulate it, but in my head, I'm thinking, well, if the solder paste soldered every other component on the board perfectly, and one component is the difficult to solder component, it's fair to say the solder paste doesn't stink. It's fair to say that you've got a difficult to solder component for some reason. And that's where I say that the root cause can be divergent because we don't exactly know why that particular component is difficult to solder or difficult to wet. I'll stick with the theme. There's a variety of reasons. The first reason is obviously the condition of the component, meaning that it was processed improperly at the manufacturer and the plating is substandard. And the way to remedy, a down and dirty way of determining whether or not the component is solderable at all, I'm talking about surface mount components, is to take that surface mount component and try and solder it with a soldering iron, because the rapid high heat of the soldering iron will often break down an oxide layer that's preventing soldering from occurring, and you can solder it. So to paraphrase Arnold Schwarzenegger from The Predator, if it bleeds, we can kill it. If it wets, we can solder it.
I guarantee you that movie has never been referenced, not only on this podcast, but probably in the entirety of the literature for electronics manufacturing. So congratulations to you, sir.
Oh, thank you. I like that movie.
Long overdue.
So,
Schwarzenegger on soldering, coming soon.
It's not Schwarzenegger. Yeah, it solders perfectly. He actually was on Stern recently, and it was a pretty interesting interview. But anyway, I gave away. I listened to Stern too. Don't hold it against me. So when we break down the oxide layer with the rapid heat of the soldering iron, we know that there is a solderable surface there, because sometimes components are just unsolderable. Whatever contamination is present simply will prevent wetting from occurring at all. And that happens from time to time. And if you think about how a soldering iron gets heat into the component as opposed to how a reflow oven gets heat into the component, a reflow oven gets heat into the component in a very gradual way. It takes time, as opposed to the soldering iron that's essentially instantaneous. It's minutes in an oven versus seconds with the soldering iron. So that often is an indicator that we've got something here that we can work with. So that's an easy way for us to know, can we start to work on the one thing that we can manipulate in the process, profile, to enhance wetting. So then the engineer and our tech team will busily work together on profiles, and it might not come as a surprise if hot, short heating cycle with a soldering iron breaks down oxide. It's our experience that a hot, short profile will often improve outcomes as it relates to wetting. It'll improve wetting as a matter of course, and for two reasons. The first reason being that you don't reoxidize the components in the reflow oven. So adding thermal energy to a PCB increases the oxidation rate of the alloys that are on the board. The oxides have to be removed by the flux chemistry in order for the intermetallics to be formed and for a solder joint to be formed. So by not throwing a ton of heat at a assembly in a soak zone, for example, you're not producing all those oxides, and then the flux has an easier job, and there's more there to break down whatever was impeding soldering to begin with. Short, hot profiles, most profiles will, they target about a 4-minute time to peak. We'll go as short as 3 minutes, or short as any component on the board can withstand without causing thermal damage. And obviously this requires a lot of expertise, understanding the oven that's in use, the thermal mass of the assembly, what paste chemistry we're working with, even what alloy can have some impact on all that stuff. A non-silver bearing alloy might not wet as well as a silver bearing alloy, as silver tends to enhance wetting performance of alloys. And that would be true of any form, whether it be wave solder, wire solder, or SMT. So that's one of the things that we run into fairly regularly, and I would encourage listeners, if it's one component that's not soldering, to investigate the component and not the paste if the rest of the board is meeting your quality requirements. We have to really focus on where the problem is. And we're more than happy to provide counsel. It's just that it's probably not the paste. Sometimes, but not usually. So that's the anecdote from the field. That's very, very common, actually. It probably get that call 1 or 2 times a week to one of the guys around the globe that are supporting the effort. And wetting is kind of a catch-all term for soldering. We all want our well-wetted joints, but you'll hear that term expressed when you don't get full barrel fill, for example. People will say, well, it's not wetting properly. Well, and this is where the confusion lies in us as a manufacturer trying to provide guidance and diagnose a problem, is really drilling down through the verbiage. And I'm sure you've run into this too, where people use variety of terms around the globe to express the same idea. Some people still say screen printing. Well, screens haven't been used in solder paste for many moons. It's really stencil printing would probably be a more accurate term. But that's just an example of how these legacy terms carry over and can sometimes really cloud the conversation, because one guy thinks he's talking about one thing and he's actually talking about something related but different. There's also different types of wetting issues. So there's the non-wet condition, and I'll describe that as meaning the component wasn't solderable, or the solder was inadequate to solder the substrates. So the flux selection, for example, wasn't aggressive enough to wet to whatever it is that we want to wet to. I got a call this week for somebody who wanted to solder to plate aluminum. Well, plate aluminum requires basically straight hydrochloric acid in order to remove the aluminum oxides and make this and have a chance of even wetting the surface. So to submit a solder paste sample of no clean, it would just turn into a ball and wouldn't solder at all. So that would be a non-wet situation where there just isn't the right product or the right flux for the given application. And then there's a de-wetting condition. So de-wetting is where wetting occurred and then it retreated and it came back from whatever it was wetting to for a variety of reasons. But the primary reason is usually exhaustion of the flux. So flux does a couple of different things. It not only breaks down the oxides and removes grease and oils to permit the intermetallics to form, but it also has what we call blanketing agents in it that prevent the surface from reoxidizing. So if you exhaust all of that, reoxidation occurs because, as I mentioned earlier, throwing heat at it, you get oxide layer, and then eventually there's just not enough blanketing agent or activator left, and the solder will retreat from where it had originally wetted. So you normally would see that on a high thermal mass assembly where a lot of heat had to get thrown at a board and you have a small deposit, for example. A small deposit of solder paste doesn't have as much flux relative to the amount of surface area of the solder, and therefore it exhausts itself just cleaning the spheres in the solder paste itself, and then there isn't enough stuff to endure a long hot profile, and you'll get a de-wet situation. And a trained operator or a trained quality inspector will be able to differentiate between the two. They're pretty clearly different. Evidence of wetting is a de-wetting condition. A non-wet condition is, you can see it just turned into a ball and didn't really go anywhere. And depending upon what we see, obviously the remedy would be different. In the case of a non-wet condition, we might recommend a different product, something that's got more activity. But, whenever we change the chemistry to accommodate something like that, our world is a this for that, a quid pro quo. Anytime I increase the activity of a product, of a flux, and I'm referring to solder paste pretty much specifically, we increase its reactivity. So solder powder and flux medium are in a jar. We refrigerate them to slow down the chemical reactions between the flux medium and the metal powder. Take it out of the fridge, allow it to come to room temperature. Those chemical reactions start to accelerate due to the increased temperature, and then you stick it in an oven, and those chemical reactions explode, and everything happens really, really fast. So if I make a paste more active, I'm making it more reactive, where it reacts with itself, and you may lose other attributes of the product in the pursuit of a more aggressive material. I could make a solder paste that would wet to a difficult to wet surface, but it would not be something that I could ship around the globe and expect the customer to open it and not have it be a solid mass where everything is reacted with one another and it's just turned into a jar of cement. It's happened. So we have to find the balancing act between usability, activity, and then marketability, the ability to bring this product to market. Particularly when you sell through distribution channels, we as the factory will ship that product to the distributor, and then we've kind of lost control of it. We train our distributors to handle products correctly, but Father Time marches on, and so product may sit in inventory due to a canceled order or a project that gets pushed out, and product ages. So bringing a fresh product to market can be difficult when you're going through, a more convoluted supply chain. So we have to make sure that the product is stable yet active enough to meet, I would say 80% of the market requirements. So that's how we have to balance things and how we can address a non-wet. And then a dewetting condition is typically related to process, typically profile related, typically time at temperature related, but be it surface mount, be it wave, be it hand soldering. There are a lot of other variables to consider in that calculation as well. What's the surface finish? Different surface finishes are more durable as it relates to storage. So an OSP surface finish is not going to have the same wetting characteristics over time as an ENIG surface finish will, as the OSP finish will degrade more rapidly, which will introduce wetting issues simply because the underlying copper becomes oxidized. And we're dealing with a finite volume of solder paste here. And once the flux molecules are exhausted, they're gone. And the dewetting condition will occur, or a non-wetting condition will occur. We really kind of have to play investigator a little bit in those circumstances to figure out what's happening in terms of what root cause is. Is it a handling issue? Is it a bareboard manufacturing issue? Is it a materials issue on our end? Did something get screwed up during the production? So you have to ask a lot of probing questions. You have to hope that the customer is frank in telling you that, we left those boards out over the weekend and the air conditioner broke and it was 100 degrees in here for a couple hours, but now help me fix it. As opposed to not sharing pieces of information that are critical to us making an accurate diagnosis.
Tim, what about ultrafine pitch?
Something that's getting more and more attention is the incorporation of finer and finer mesh materials. Right now, you find the finest mesh powders in jetting applications, but we're running into applications where people are using type 6 powders with 3 mil stencils. And these deposits are as small as the period at the end of the page. They have to be right. There's a phenomena, this one's called graping, because when the solder paste is reflowed, it doesn't coalesce and it looks like a bunch of grapes. And really, that's a wetting defect. What happens is that because the deposit is so small, and as I had mentioned earlier, the amount of flux that's available is finite, there isn't enough activator in the flux to break down the oxide layer on the surface of the powder, because type 6 powder will have 4 times the surface area of a type 4 powder. And so with the long gradual heat process required for a reflow profile, that oxide layer gets thicker and thicker. The flux is trying to break it down until it gets to the point where the flux is completely exhausted and coalescence can't occur. As we've said on numerous articles and information that's available on our website, the last variable you want to change, in our opinion, in order to improve fine pitch print results is the mesh size and the solder paste. And unfortunately, it's usually the first thing an engineer wants to change, because I think the perception is that it's an easy way out. And I can give you 4 or 5 other things that in our studies have indicated that would improve fine pitch print results without having to drop the mesh size down, which ultimately will save you a bunch of wetting-related headaches. That's wetting. That's what happens to us when we're sitting in our offices fielding wetting-related issues from our customers. You know, just to summarize briefly, fresh boards, fresh components, fresh solder paste are cheap insurance policies to minimize wetting-related defects.
Listeners who don't want to wait for the next episode of the Screwups to hear more from Tim, I believe they can track you down at SMTAI in a couple weeks. Is that correct?
That's true. I will be attending SMTAI, good Lord willing, at booth 406. Bring us your problems. We want to hear about them. We want to give you as much information as we can so that we can get customers where they need to be.
Okay, and that's Surface Mount Technology Association International in Rosemont, north of Chicago, and it's the week of September 23rd. And that concludes this episode of the Screwups. I want to thank Tim O'Neill from AIM Solder for coming on, and thanks to our sponsor, Zestron Corporation, the leading provider of high-precision cleaning products. Be sure to visit Zestron at SMTAI booth 623. For PCB Chat, I'm Mike Buetow. Have a nice day.